Somewhere out there in the vast cosmos, there's a place where everything we think we know about reality simply falls apart. A place where time itself comes to a grinding halt, where light vanishes into nothingness, and where space gets twisted and warped like a piece of fabric being stretched to its breaking point. This isn't science fiction. This place actually exists, and we call it a black hole. You know what's absolutely incredible about this? Right now, as you're watching this video, there are millions of these cosmic monsters scattered throughout our universe, quietly bending the very fabric of space and time around them. Some are no bigger than a city, but weigh more than our entire sun. Others are so massive they could swallow billions of stars without even noticing. Today, here on Exploring the Universe, we're going to take a journey into the heart of these mysterious giants and uncover some mind-blowing truths. How do they actually twist and distort the fabric of reality itself? What would really happen to you if you somehow found yourself falling into one? And how did Albert Einstein manage to predict their existence more than a century ago, long before we had any proof they were real? Here's something that might surprise you. Einstein himself didn't even believe black holes could actually exist when his equations first predicted them back in 1915. He thought the math was just playing tricks on him. Little did he know that nature had already been crafting these incredible objects for billions of years, patiently waiting for us to develop the technology to finally see them. The story of how we discovered black holes is actually a tale of human curiosity pushing against the impossible. For decades, scientists could only theorize about these invisible giants, using nothing but mathematics and imagination to explore places where no human could ever venture. It wasn't until 2019 that we finally captured our first real photograph of a black hole. And when that image appeared on screens around the world, it looked exactly like Einstein had predicted a century earlier. Before we dive deeper into this cosmic adventure, make sure to hit that like button and subscribe to Exploring the Universe so you won't miss any of our incredible discoveries about the cosmos. The story of every black hole begins with a cosmic tragedy, the death of a massive star. Picture a star that's at least 8 times heavier than our sun, burning bright in space for millions of years. But here's the thing about stars. They're constantly fighting a battle against their own gravity. For most of a star's life, it's like a perfectly balanced tug-of-war match. On one side, you have nuclear fusion in the star's core, creating tremendous outward pressure that tries to blow the star apart. On the other side, you have gravity pulling everything inward with incredible force. As long as the star has fuel to burn, this cosmic wrestling match stays even. But then comes the moment every massive star dreads. It runs out of fuel. Imagine a car suddenly running out of gas while going up a steep hill. The engine stops, and gravity takes over completely. In the star's case, this happens in a matter of seconds. The core temperature drops, fusion stops, and suddenly there's nothing left to hold back the crushing weight of the star's own mass. In its final moments, the star collapses under its own weight so violently that it creates something almost impossible to imagine, a point so incredibly dense that not even light can escape from it. This invisible boundary around that point is what we call the event horizon. Think about it this way. Light is the fastest thing in the universe. Nothing can outrun it. But inside this boundary, gravity becomes so powerful that it grabs hold of light itself and pulls it back down, like trying to throw a ball up while standing at the bottom of an infinitely deep well. Here's where it gets really fascinating. The brilliant physicist Stephen Hawking once said something that completely changed how we think about these cosmic monsters. Black holes are not eternal prisons. They emit radiation and can evaporate. This was revolutionary because for years, scientists thought that once something fell into a black hole, it was gone forever. Hawking showed us that black holes actually leak energy very slowly over incredibly long periods of time. Did you know that if our sun suddenly turned into a black hole right now, Earth would continue orbiting it just like normal? The gravitational pull would be exactly the same. Of course, we'd all freeze to death in the darkness, but our planet wouldn't get sucked in. This happens because black holes don't actually suck things in like cosmic vacuum cleaners. They're more like incredibly steep hills in the fabric of space. You only fall in if you get too close to the edge, or if you're moving too slowly to maintain your orbit. It's the same reason the International Space Station doesn't fall back to Earth. It's moving fast enough to keep circling around our planet. The really wild part is that every black hole started as a star that once shone brightly in someone's night sky, perhaps even helping ancient civilizations navigate across oceans or mark the changing seasons. Now, instead of giving light to the universe, these stellar remnants have become invisible guardians of cosmic secrets, warping space and time in ways that continue to challenge everything we thought we knew about reality. Einstein showed us something absolutely revolutionary, that space and time aren't separate things at all. They're woven together like threads in a cosmic fabric that stretches across the entire universe. And a black hole? Well, imagine dropping a bowling ball right in the middle of a stretched-out trampoline. The heavier the ball, the deeper the dent it creates. Before Einstein came along in the early 1900s, everyone thought space was just empty nothingness, a stage where planets and stars performed their cosmic dance. Time was seen as something that ticked along steadily, like a universal clock that never changed its pace. But Einstein had a completely different vision. He realized that massive objects actually bend and twist this invisible fabric of space-time around them. It's like when you're walking on a wooden floor and it creaks under your weight. The floor bends slightly, even if you can't see it happening. Now imagine that floor is the fabric of reality itself, and instead of just creaking, it's creating invisible valleys and hills that guide everything around it. Here's where black holes become the ultimate cosmic dancers. When a massive star collapses into a black hole, it's like taking that bowling ball on the trampoline and replacing it with something impossibly heavy. Imagine a cannonball made of pure lead, but compressed down to the size of a marble. The dent it creates becomes so deep and steep that it's more like a funnel with no bottom. But here's the part that really bends your mind. Time itself gets caught up in this cosmic dance. The closer you get to a black hole, the slower time moves compared to everywhere else in the universe. It's not just a theory anymore. We've actually measured this happening. Here's a mind-blowing curiosity. If you fell into a black hole, time would pass more slowly for you than for someone watching you from far away. Picture this scenario. You and your best friend are floating in space near a black hole. Your friend stays safely far away while you decide to take a closer look. As you approach the black hole, something incredible happens. From your friend's perspective, watching through a telescope, you start moving in slow motion. Your movements become sluggish. Your voice gets deeper and slower, like a recording being played at half speed. But here's the really wild part. From your perspective, everything feels completely normal. Your watch ticks at the same rate, your heartbeat feels the same, and you don't notice anything unusual about time. Meanwhile, when you look back at your friend, you see them moving incredibly fast, like someone hit the fast-forward button on their life. This isn't science fiction. It's a real effect called gravitational time dilation. NASA has to account for this when they send signals to and from spacecraft. Even here on Earth, time moves slightly slower at sea level compared to the top of a mountain, because Earth's gravity is just a tiny bit stronger closer to the center. The most amazing part is that Einstein figured all this out just by thinking about it, decades before we had the technology to prove he was right. He imagined riding alongside a beam of light and asked himself what the universe would look like from that perspective. Those thought experiments led him to realize that space and time dance together in ways that our everyday experience never reveals. When you really think about it, every step you take is actually a journey through both space and time simultaneously. You're not just moving from one place to another. You're traveling through the four-dimensional fabric of space-time itself. And black holes are the ultimate proof that this invisible cosmic dance floor can be bent, twisted, and warped in ways that challenge everything we thought we knew about reality. Imagine standing at the edge of a cliff so tall that once you step off, there's absolutely no way back up. That's exactly what the event horizon is like. An invisible boundary around a black hole where the rules of escape simply don't apply anymore. Cross that line, and gravity becomes so overwhelmingly powerful that even time itself gets twisted and bent beyond recognition. The event horizon isn't a physical wall or barrier that you could touch. It's more like an invisible line drawn in space where the laws of physics shift dramatically. Think of it as the ultimate cosmic speed limit checkpoint. To escape from inside this boundary, you'd need to travel faster than light itself. And since nothing in the universe can do that, anything that crosses over is trapped forever. But here's where things get really strange and unsettling. As you approach this point of no return, your body would start experiencing something that scientists have given a rather colorful name: spaghettification. Just like the name suggests, you'd get stretched out like a piece of spaghetti. But the reason why is both fascinating and terrifying. Picture yourself falling feet first toward a black hole. The gravity pulling on your feet becomes significantly stronger than the gravity pulling on your head because your feet are closer to the black hole's center. This difference in gravitational pull creates what's called a tidal force. It's the same force that causes ocean tides on Earth, but here it's powerful enough to literally stretch your body. At first, you might just feel like you're being gently pulled apart, similar to the sensation of hanging from a pull-up bar. But as you get closer to the event horizon, this stretching becomes more and more intense. Your body would gradually elongate, becoming thinner and longer until you'd look like a human noodle floating through space. What makes this even more mind-bending is how time plays into the whole experience. Remember that friend we talked about earlier, watching you from a safe distance? From their perspective, something incredible and disturbing happens as you approach the event horizon. They'd see you slowing down more and more, like you're moving through invisible molasses. The light coming from your body would also start shifting toward the red end of the spectrum, making you appear redder and dimmer. Eventually, from your friend's viewpoint, you'd seem to freeze completely at the event horizon, slowly fading from view as your light becomes too red and weak to see. But here's the really wild part. From your perspective, you'd pass right through the event horizon without even noticing it, continuing your journey toward the center. Hollywood actually got this science remarkably right in the movie Interstellar. The filmmakers worked closely with physicist Kip Thorne to create one of the most scientifically accurate depictions of a black hole ever put on screen. When the characters approach the massive black hole called Gargantua, they experience real-time dilation effects. What feels like minutes to them translates to years passing for people back on Earth. The movie also showed how the event horizon isn't just a point in space, it's a point in time as well. Once you cross it, your future becomes completely disconnected from the rest of the universe. You can receive light and information from outside, watching the universe age rapidly around you, but you can never send any signal back out to let anyone know what you're experiencing. Perhaps the most haunting aspect of the event horizon is that it represents the ultimate one-way journey. Every human exploration throughout history, from crossing oceans to landing on the moon, has been about going somewhere and coming back to tell the story. But crossing an event horizon breaks that fundamental pattern of human exploration. You become an eternal traveler with no way to share your discoveries with the rest of humanity. Scientists sometimes call the event horizon the surface of no return. And there's something deeply poetic about that phrase. It reminds us that even in our vast, explorable universe, there are still boundaries that represent the absolute limits of human experience, places where curiosity leads to the ultimate sacrifice of never being able to return home. At the very heart of every black hole lies something that makes even the world's greatest scientists scratch their heads in confusion. It's called a singularity. A point where all the mathematical equations that describe our universe simply break down and stop making sense. Even Einstein, the genius who predicted black holes in the first place, had no idea what actually happens in there. Think about the most confusing math problem you've ever encountered. Now imagine that problem multiplied by infinity, and you'll start to get a sense of what physicists face when they try to understand singularities. It's like trying to divide a number by 0 on a calculator. The screen just shows error, because mathematics itself can't handle the situation. Here's what we think we know about singularities, and trust me, it's going to sound absolutely wild. Picture taking all the mass that used to be a massive star, something that might have been millions of times wider than Earth, and crushing it down into a point that has 0 size but infinite density. Your brain probably just did a little flip trying to process that, and that's completely normal. Even physicists get headaches thinking about it. To understand how strange this is, let's use an analogy. Imagine you have a sponge that you keep squeezing smaller and smaller. At some point, you can't squeeze it anymore because the material has limits. But in a singularity, there are no limits. The matter keeps getting compressed forever, creating densities so extreme that they break every rule of physics we've ever discovered. The famous physicist Kip Thorne, who worked on the movie Interstellar and is one of the world's leading experts on black holes, put it perfectly when he said, "Singularities are places where our knowledge ends." Think about that for a moment. Here we are, a species that has figured out how to split atoms, land robots on Mars, and peer billions of years into the past by looking at distant galaxies. Yet there's this thing hiding at the center of black holes that makes all our knowledge just stop working. What's even more mind-bending is that singularities might not actually be points at all. Some scientists think they could be incredibly tiny strings or loops or shapes that we don't even have names for yet. Others believe that when you get close enough to a singularity, the very concepts of space and time stop having any meaning. It's like trying to ask, what's north of the North Pole? The question itself doesn't make sense. Here's something that might keep you awake at night. According to our best theories, if you somehow survived the journey through the event horizon and the spaghettification process, you'd eventually reach this singularity. But what would you experience there? Would time stop? Would you be stretched across multiple dimensions? Would you see the entire history and future of the universe flash before your eyes? Nobody knows, and that's both terrifying and fascinating. The really humbling part is that singularities force us to confront the limits of human understanding. Throughout history, whenever we've encountered something we couldn't explain, we've eventually figured it out. We learned that lightning isn't the anger of gods, but electrical discharge. We discovered that diseases aren't caused by bad air, but by tiny organisms. We realized that the Earth isn't the center of the universe, but a small planet orbiting an ordinary star. But singularities are different. They represent a fundamental breakdown in our ability to describe reality. It's like having a map of the world with a big blank spot labeled "Here be dragons." Except in this case, the dragons might be the key to understanding the deepest secrets of existence itself. Some scientists believe that studying singularities might eventually lead us to a theory of everything, a set of equations that could explain every force and particle in the universe. Others think that singularities are nature's way of hiding information that we're simply not meant to understand. Either way, they remind us that for all our scientific progress, the universe still holds mysteries that can make even the smartest humans feel like we're just children trying to understand something far beyond our current abilities. If this kind of mind-bending content fascinates you, make sure to subscribe to Exploring the Universe so you can join us as we continue exploring all the incredible mysteries the cosmos has in store for us. The beauty of singularities is that they keep us humble. They remind us that no matter how much we learn, there will always be new frontiers to explore, new questions to ask, and new mysteries to unravel. And who knows, maybe someday, a curious person watching videos like this one will be the first to finally understand what really happens at the heart of a black hole. Now, if you thought regular black holes were impressive, wait until you hear about their absolutely colossal cousins. While typical black holes might weigh as much as a few suns, the supermassive ones are cosmic monsters that can be millions or even billions of times heavier than our sun. And here's the really wild part. They're hiding right at the heart of galaxies, including our very own Milky Way. Picture this. You know how every neighborhood seems to have that one house where everyone gathers for parties? Well, galaxies work in a similar way, except instead of a house, there's a supermassive black hole at the center that somehow keeps hundreds of billions of stars dancing around it in a cosmic choreography that's been going on for billions of years. Our own galactic neighbor has a name that sounds like it belongs in a science fiction movie. Sagittarius A star. This massive black hole sits right at the center of our Milky Way galaxy, about 26,000 light-years away from us. To put that in perspective, if you could travel at the speed of light, it would still take you 26,000 years to reach it. And here's the mind-blowing part. This cosmic giant weighs about 4 million times more than our sun. Sagittarius A star, the black hole at the center of our galaxy, has 4 million times the mass of the sun, but it's currently sleeping, for now. But don't worry, this sleeping giant isn't going to wake up tomorrow and suddenly start devouring our solar system. Sagittarius A star is what astronomers call a quiet, supermassive black hole. It's like a hibernating bear, incredibly powerful, but not actively feeding. Every now and then, an unlucky star or gas cloud wanders too close, and we get to witness an amazing cosmic light show as the material gets heated up and torn apart before disappearing forever. The story of how we discovered these galactic giants is actually one of the most exciting detective stories in modern astronomy. For decades, scientists noticed that stars near the centers of galaxies were moving incredibly fast, much faster than they should be if there was just empty space there. It was like watching cars race around an invisible racetrack at impossible speeds. Then came one of the most historic moments in astronomy. In 2019, scientists using the Event Horizon telescope managed to capture the first real photograph of a supermassive black hole. But it wasn't our own Sagittarius A star. It was an even bigger monster called M87 star, located in a galaxy 54 million light-years away. When that image appeared on computer screens around the world, showing a glowing ring of light surrounding a dark shadow, it looked exactly like what Einstein's equations had predicted more than a century earlier. The image was breathtaking and terrifying at the same time. Here was visual proof of something so massive that it could swallow our entire solar system and barely notice. The black hole in that photograph weighs about 6.5 billion times more than our sun. To put that in perspective, if our sun was a grape, this supermassive black hole would be larger than Earth itself. If a supermassive black hole is so incredibly powerful, why doesn't it just devour the entire galaxy? Are we actually safe out here? This is one of the most common questions people ask, and the answer is both reassuring and fascinating. Supermassive black holes are like cosmic anchors rather than cosmic vacuum cleaners. They don't suck everything in. Instead, they create a gravitational center that helps hold the entire galaxy together. Think of it like a giant merry-go-round in space, with the black hole as the central post that everything else spins around. We're actually incredibly safe here on Earth. Our solar system is orbiting the galactic center at a comfortable distance, moving at about 500,000 miles per hour. At this distance and speed, we're in a stable orbit that will continue for billions of years. It's the same reason the International Space Station doesn't fall back to Earth. It's moving fast enough to keep circling around our planet. But here's something that might surprise you. Supermassive black holes might actually be essential for life as we know it. Many scientists believe that these cosmic giants play a crucial role in galaxy formation and evolution. They help regulate star formation, influence the distribution of matter throughout the galaxy, and might even be responsible for creating the stable conditions that allow planets like Earth to exist. Some of these supermassive black holes are far from quiet, though. When they're actively feeding on nearby matter, they become some of the brightest objects in the entire universe, shooting jets of superheated plasma thousands of light-years into space. These active black holes, called quasars, can outshine entire galaxies and can be seen from billions of light-years away. The most amazing part is that every major galaxy we've observed has one of these supermassive black holes at its center. It's like discovering that every city on Earth has a hidden giant living underneath it, quietly shaping the way the city grows and develops. These cosmic giants have been there since the early days of the universe, silently orchestrating the grand dance of stars and planets that makes up our cosmic home. Here's where Einstein's imagination really took flight into the realm of science fiction, becoming science fact. Beyond black holes, he also theorized about something even more mind-bending: wormholes, cosmic shortcuts that could potentially take us to other places in space, or even through time itself. But here's the catch. For them to exist, they would need something called exotic energy that we haven't discovered yet. Picture this scenario. You're living in New York, and you want to visit a friend in Tokyo. Normally, you'd have to travel all the way around the curved surface of the Earth, maybe taking a plane that flies for 13 hours. But what if you could dig a tunnel straight through the center of the planet? You'd get there much faster by taking this impossible shortcut. That's essentially what a wormhole would be, except instead of digging through Earth, you're creating a tunnel through the fabric of space-time itself. Imagine the universe as a piece of paper that you fold in half. A wormhole would be like poking a hole that connects two distant points without having to travel the entire distance along the surface. The brilliant scientist and storyteller Carl Sagan once said something that perfectly captures the wonder of this concept. Science is not only about what we know, but about what we can still dream. And wormholes represent one of the most incredible dreams that physics has ever dared to imagine. Einstein discovered the mathematical possibility of wormholes almost by accident back in 1935, when he was working with his colleague, Nathan Rosen. They were studying the equations of general relativity and found something unexpected. The math suggested that black holes might actually be connected to white holes, which would be the exact opposite of black holes, spewing matter and energy out instead of pulling it in. The connection between these two cosmic opposites would create what they called an Einstein-Rosen bridge, but everyone else started calling them wormholes because they work like the tunnels that worms dig through apples. A worm doesn't have to crawl all the way around the apple's surface to get from one side to the other. It just burrows straight through the middle. But here's where reality gets in the way of our cosmic dreams. For a wormhole to actually work as a shortcut, it would need to be held open by something that physicists call exotic matter or negative energy. Think of it like trying to keep a tunnel from collapsing while you're digging it. You need some kind of support structure. But in this case, the support would need to have properties that we've never observed anywhere in the universe. This exotic matter would need to have negative energy density, which sounds like something out of a fantasy novel. Regular matter has positive energy and creates gravity that pulls things together. But exotic matter would have negative energy and would push things apart, fighting against gravity's tendency to collapse the wormhole tunnel. The frustrating part is that every time physicists run the calculations, they find that wormholes would be incredibly unstable. Even if you could create one, it would probably collapse faster than light could travel through it. It's like trying to send a message through a tunnel that caves in before your words can reach the other end. Some scientists have proposed that advanced civilizations might be able to engineer wormholes by manipulating the quantum properties of space-time itself. They imagine cosmic construction projects where beings with technology millions of years more advanced than ours could essentially grab the fabric of reality and fold it like origami, creating permanent shortcuts between distant parts of the universe. There's also the mind-bending possibility that wormholes could connect not just different places, but different times. You could theoretically enter a wormhole on Earth in 2025 and emerge near Alpha Centauri in the year 1950. This opens up all sorts of time travel paradoxes that make scientists' heads spin. What happens if you go back in time and prevent your own birth? Would the universe create some kind of cosmic course correction? Or would you create an alternate timeline? Hollywood has had a field day with wormholes, from the movie Contact, where Jodie Foster travels through one to meet aliens, to Interstellar, where the characters use them to reach distant planets. While these movies take creative liberties, they're actually based on real physics concepts that Einstein and other brilliant minds developed through pure mathematical reasoning. The most tantalizing part about wormholes is that they might already exist naturally in the universe. Some theories suggest that the Big Bang itself might have created tiny wormholes that are constantly popping in and out of existence at the quantum level. These would be far too small for anything larger than a subatomic particle to pass through. But they hint that the universe might be far more connected than we ever imagined. Even if we never discover naturally occurring wormholes or figure out how to create them artificially, they've already served an incredible purpose. They've pushed us to think about space and time in completely new ways, challenging our assumptions about what's possible and reminding us that the universe is far stranger and more wonderful than our everyday experience suggests. The dream of wormholes represents humanity at its best. Our endless curiosity, our refusal to accept limitations, and our determination to explore even the most impossible-seeming frontiers. Whether they exist or not, wormholes have already expanded our minds and opened up new ways of thinking about our place in the cosmos. Here's one of the biggest mysteries keeping physicists awake at night. If a black hole destroys everything that falls into it, what happens to the information that made up those things? Does it just vanish forever into cosmic nothingness? Now, when physicists talk about information, they're not talking about your text messages or your favorite photos. They mean something much more fundamental. The basic properties that make you, you. Every atom in your body, every particle that makes up those atoms, every quantum property that defines how those particles behave. All of that is information in the cosmic sense. Think about it like this. If I gave you a detailed enough description of every single particle in a book, where each atom is located, how fast it's moving, what it's made of, you could theoretically reconstruct that exact book perfectly. That description would be the book's information. Now, here's where things get mind-bending. According to the fundamental laws of physics, information can never be completely destroyed. It can be scrambled, hidden, or transformed, but it should always exist somewhere in some form. This creates what scientists call the information paradox, and it's been driving brilliant minds crazy for decades. Picture this scenario. You take that book and throw it into a black hole. From our perspective outside, the book disappears forever, seemingly taking all its information with it. But wait, if information can't be destroyed, where did the book's information go? Stephen Hawking made this puzzle even more complicated back in 1974, when he discovered something incredible. He realized that black holes aren't completely black after all. They actually emit a faint radiation, now called Hawking radiation, which means they slowly evaporate over incredibly long periods of time. Hawking's theory suggests that black holes can actually leak information as they evaporate, but it's still a complete mystery how this works. Here's where the story gets really wild. Hawking radiation appears to be completely random, like cosmic static with no meaningful pattern. So if a black hole eventually evaporates completely through this radiation, what happens to all the information that fell into it over its lifetime? Does it come out encoded in that seemingly random radiation, or does it disappear forever, breaking one of the most fundamental rules of physics? This isn't just an abstract problem for theoretical physicists sitting in their offices. This paradox strikes at the heart of how we understand reality itself. It's like discovering that the universe might have a giant cosmic shredder that can permanently erase parts of existence. That would fundamentally change everything we think we know about how the cosmos works. Some of the world's smartest scientists have proposed absolutely wild solutions to this puzzle. One idea suggests that information gets encoded on the black hole's event horizon, like a cosmic hard drive storing everything that's ever fallen in. From this perspective, nothing actually falls into the black hole. It just gets compressed and stored on the surface in a way that looks like it disappeared. Another mind-bending theory proposes that when you fall into a black hole, you create copies of yourself. One copy appears to burn up at the event horizon, while another copy continues falling toward the singularity. This would solve the information problem, but it creates the disturbing possibility that there could be multiple versions of you experiencing different fates simultaneously. Then there's the idea that black holes might be connected to other regions of space-time through hidden cosmic tunnels. In this scenario, information that falls into a black hole in one part of the universe might emerge somewhere completely different, possibly even in a parallel universe. It's like having a cosmic recycling system that we're not even aware of. If information truly cannot be destroyed, does the universe somehow find a way to preserve it, even inside a black hole? This question touches on something profound about the nature of existence itself. It suggests that the universe might have built-in safeguards to prevent anything from being completely erased. Every moment of your life, every thought you've ever had, every decision you've made, all of that information might be permanently woven into the fabric of reality in ways we don't yet understand. The information paradox also raises fascinating questions about the nature of memory and identity. If all the information that makes you who you are could theoretically be recovered from Hawking radiation billions of years in the future, would that reconstructed version still be you? Would they have your memories, your personality, your dreams and fears? Some scientists believe that solving this paradox will require a complete revolution in how we think about space, time, and reality. It might lead us to discover that the universe is far more interconnected than we ever imagined, with hidden networks of information flowing in ways that transcend our current understanding of physics. The beautiful thing about this mystery is that it shows us how much we still don't know. Here we are, a species that has figured out how to split atoms and peer back to the beginning of time, yet we're still puzzled by fundamental questions about what happens to information. It's humbling and exciting whether the universe preserves information through quantum mechanics, parallel dimensions, or cosmic bookkeeping systems we haven't discovered yet. One thing is certain. The information paradox reminds us that reality is far stranger and more mysterious than our everyday experience suggests. And somewhere in that mystery might lie the keys to understanding the deepest secrets of existence itself. We're living in absolutely incredible times for black hole research. With revolutionary new technologies emerging every year, we're getting closer and closer to unraveling these cosmic mysteries that have puzzled humanity for generations. Telescopes like the Event Horizon Telescope and ambitious future missions might finally show us what really happens beyond the event horizon. Just think about how far we've come in such a short time. A century ago, black holes existed only as strange mathematical curiosities in Einstein's equations. Most scientists, including Einstein himself, didn't even believe they could be real. Fast forward to today, and we're not just observing them from billions of miles away. We're actually taking their pictures and watching them devour stars in real time. The Event Horizon Telescope represents one of humanity's most ambitious scientific collaborations. Picture this. Scientists took telescopes from all around the world, from Hawaii to Chile to Antarctica, and linked them together to create a virtual telescope the size of our entire planet. It's like turning Earth itself into one giant cosmic camera lens. The resolution is so incredible that if you had this kind of telescope vision, you could read a newspaper in New York while standing in Los Angeles. But here's what's really exciting about the future. We're just getting started. Scientists are already planning to add even more telescopes to this global network. And some visionaries are talking about putting telescopes in space to create an even larger virtual observatory. Imagine having a telescope array that spans not just Earth, but extends out into the solar system itself. Scientists have already simulated black holes in laboratories, using ultra-cold atoms and lasers. This might sound like science fiction, but it's happening right now in labs around the world. Researchers have figured out how to create tiny analogs of black holes using clouds of atoms cooled to temperatures colder than outer space and manipulated with precisely controlled laser beams. These laboratory black holes behave remarkably similarly to the real cosmic giants, allowing scientists to test theories about Hawking radiation and information paradoxes without having to travel 26,000 light-years to our galactic center. The implications of this kind of research are absolutely staggering. These artificial black holes are helping us understand fundamental questions about quantum mechanics, gravity, and the nature of space-time itself. It's like having a cosmic laboratory right here on Earth where we can poke and prod at the mysteries of the universe in ways that would be impossible with real black holes. In the future, understanding black holes could lead us to new forms of energy, interstellar travel, or even the answer to the origin of the universe itself. Think about how every major scientific breakthrough has eventually led to technologies that transformed human civilization. When scientists first discovered electricity, they had no idea it would eventually power our cities and connect us through the internet. When researchers first split the atom, they couldn't have imagined it would lead to both nuclear power and medical imaging that saves countless lives. Black hole research might follow a similar path. Some scientists believe that understanding how black holes manipulate space-time could eventually lead us to revolutionary new forms of energy generation. Imagine if we could harness even a tiny fraction of the immense power that black holes wield. A black hole the size of a marble would contain more energy than all the nuclear weapons ever built. There's also the tantalizing possibility that black hole research could unlock the secrets of faster-than-light travel. While we can't break the speed of light directly, understanding how black holes warp space-time might teach us how to bend reality itself, creating shortcuts through the cosmos that would make interstellar exploration possible within human lifetimes. Future space missions are already being planned that will take black hole research to the next level. Scientists are designing spacecraft that could fly much closer to black holes than ever before, equipped with instruments sensitive enough to detect the subtle ways these cosmic giants influence everything around them. Some proposals even include missions that would study the supermassive black hole at our galaxy's center from distances that would reveal details we've never seen before. Perhaps most exciting of all, black hole research might hold the key to understanding the very beginning of our universe. Some theories suggest that the Big Bang itself might have been related to black hole physics, and that studying these cosmic phenomena could help us understand how everything we know came to exist in the first place. The next decade is going to be absolutely revolutionary for black hole science. We're developing artificial intelligence systems that can analyze the enormous amounts of data these telescopes collect, finding patterns and connections that human scientists might miss. We're building quantum computers that can simulate black hole physics in ways that were impossible just a few years ago. We're even planning to send tiny spacecraft to the nearest star system, and those missions will test technologies that could eventually be used to study black holes up close. Black holes are so much more than cosmic destroyers. They're gateways to the universe's greatest mysteries, and who knows, maybe someday they'll lead us to entirely new frontiers of science and space exploration. The beautiful thing about scientific research is that it always leads us to places we never expected to go. Every answer we find about black holes opens up 10 new questions we didn't even know we should be asking. We're standing at the edge of a new golden age of discovery, where the most extreme objects in the universe might teach us things about reality that we can't even imagine yet. The future of black hole research isn't just about satisfying our curiosity. It's about pushing the boundaries of what it means to be human. These cosmic giants are challenging us to think bigger, dream bolder, and reach further than ever before. And in doing so, they're preparing us for a future where the impossible becomes possible, and where the mysteries of the cosmos become the foundations of tomorrow's technologies. You know, there's something almost poetic about how we've come to understand black holes. For centuries, humans looked up at the night sky and saw only points of light scattered across the darkness. We had no idea that hidden among those distant stars were forces so powerful they could literally bend the fabric of reality itself. Think about it for a moment. When Albert Einstein first proposed his theory of general relativity back in 1915, he was essentially telling us that space and time weren't the rigid, unchanging stage we thought they were. Instead, they were more like a vast, invisible ocean that could be stirred and twisted by massive objects. And nowhere is this more dramatic than around black holes. But here's what truly fascinates me about these cosmic giants. We often think of them as destroyers, as cosmic vacuum cleaners that devour everything in their path. And yes, they do that. But they're also creators, sculptors of the universe on the grandest scale imaginable. Every major galaxy we've observed has a supermassive black hole at its heart. And these aren't just sitting there doing nothing. They're actively shaping how stars form, how galaxies evolve, and even how matter flows through the cosmos. Consider our own Milky Way galaxy. At its center sits Sagittarius A star, a black hole with the mass of 4 million suns. It's been there for billions of years, quietly orchestrating the dance of hundreds of billions of stars around it. Without its gravitational influence, our galaxy might have never formed the beautiful spiral arms we see today. In a very real sense, that black hole helped create the conditions that eventually led to our solar system, our planet, and ultimately to us sitting here contemplating its existence. The more we learn about black holes, the more we realize they're not just cosmic oddities. They're fundamental to how the universe works. They regulate star formation in galaxies. They help distribute heavy elements throughout space, and they might even play a role in the mysterious dark energy that's driving the universe's expansion. Some scientists now believe that understanding black holes completely might be the key to unlocking a unified theory of everything, connecting the quantum world of the very small with the cosmic realm of the very large. And here's something that gives me chills every time I think about it. We're living in the first generation of humans who have actually seen a black hole. When the Event Horizon Telescope captured that first image of the black hole in Galaxy Messier 87 back in 2019, it wasn't just a scientific triumph. It was a moment when humanity finally laid eyes on something that had existed only in our equations and imagination for over a century. But perhaps the most mind-bending aspect of black holes is how they challenge our understanding of information and reality itself. If you throw a book into a black hole, what happens to all the information contained in that book? Does it disappear forever? Or does the universe find some way to preserve it? This might sound like a philosophical question, but it's actually one of the most important problems in modern physics. The answer could revolutionize our understanding of how reality works at its most fundamental level. Some physicists think that information that falls into a black hole gets encoded on its surface, like a hologram. Others believe it gets released slowly through Hawking radiation as the black hole evaporates. And a few even suggest that falling into a black hole might transport information to other regions of space-time, possibly through those theoretical wormholes we talked about earlier. What strikes me most is how black holes represent the ultimate frontier of human knowledge. They exist at the intersection of our greatest theories, the general theory of relativity and quantum mechanics, two frameworks that have revolutionized our understanding of the universe but still don't play well together. Black holes are the places where these theories meet, clash, and perhaps point towards something even more profound. The future of black hole research is incredibly exciting. We're developing new telescopes that will give us even sharper images of these cosmic monsters. We're building gravitational wave detectors that can hear the space-time ripples created when black holes collide. We're even conducting experiments in laboratories, using ultra-cold atoms and lasers to create analogs of black holes that we can study up close. But beyond the science, there's something deeply humbling about black holes. They remind us that despite all our technological achievements and scientific discoveries, we're still just beginning to understand the universe we live in. They represent mysteries that stretch our imagination and challenge our assumptions about reality itself. And maybe that's the most beautiful thing about black holes. They're not just objects in space, they're invitations to wonder, to question, to push the boundaries of what we think is possible. They remind us that the universe is far stranger and more magnificent than we ever dared to imagine. So as we stand here in the 21st century, looking out at a cosmos filled with these incredible cosmic architects, we're left with a profound question. These black holes have been shaping the universe for billions of years, creating the very conditions that allowed stars to shine, planets to form, and life to emerge. They've been the hidden sculptors of reality, working on timescales so vast that entire civilizations could rise and fall in what amounts to a single moment in their existence. What do you think? As we continue to unravel the mysteries of these cosmic giants, as we develop new technologies to study them, and as we perhaps even learn to harness their incredible power, are we moving toward a future where we might not just understand black holes, but actually work alongside them as partners in shaping the cosmos? The universe has been telling us its secrets through black holes for billions of years. Now finally, we're learning to listen. And the conversation has only just begun. Join us on this incredible journey of discovery. Subscribe to Exploring the Universe, hit that notification bell, like this video, and share it with fellow cosmic explorers. Together we'll continue to uncover the mysteries of our magnificent universe. Until next time, keep looking up and keep wondering.